Hi, everyone. Today we have Antigoni as our speaker. She's currently a research head at JP Morgan AI Research. Yeah, okay, sounds good now. Thank you. So today she's going to talk about her work, PrimeMatch, privacy preserving stock inventory matching. Let's welcome her.
Okay, great. So today I'm going to talk to you about something practical that we put in production in JP Morgan and involves secure computation. Wait, I need the presentation mode. How can we eliminate this? Okay. So let me start. Oh, wait for a second, guys. We have an issue here. Will you press close?
Yeah, I'm trying to.
Oh, no, it's not.
Okay.
By the way, it was this one. You were holding the wrong remote. Okay, so let me specify the problem first. So what's a current process that we have at the bank is the following. So every day, the bank has a list of their inventory. What is this inventory? It's like a bunch of stocks, okay? It can be like Google, Microsoft. So here I put some fake names, A, B, C, whatever. And then you want to buy or sell a stock. And this is the number of shares that you want to get from that stock, okay? So imagine that the bank has its own inventory, and every day they send this inventory to a lot of clients, which are usually hedge funds. And the clients look at the list, and if they want something, they come back to us and they say, hey, I want to buy this or I want to sell this, okay? So this is how it works today. However, some clients raise some concerns about this because let's say I'm the bank and I bought yesterday from you, like, let's say 100 shares or 100 million shares of Apple, okay? I bought this yesterday. So today in my list, I add this that I bought from you yesterday, right? So now some clients came and say like, okay, now your inventory is increased a lot, and maybe the other clients can realize that this came from us, that we gave this to you yesterday, okay? So apparently some hedge funds are trading more some symbols than other ones. So they're concerned that there's a leakage, that, for example, maybe we can leak that we got this from specific clients the previous days, okay? So there was this concerns. And what we did for that, we did this last summer. So instead of sending our like list in the clear, we are sending it with some differential private noise. I'm not going to talk about this today, but imagine that at the beginning, we have the whole inventory of the bank. And then because like I told you earlier that we are publishing this list every day, but we cannot publish the raw list because of some regulations, we have to remove some things. So think that it's reduced by some small amount. So in version 2, what we are really sending to the clients is a reduced inventory, okay? And in version 3 is the reduced inventory with some differential private noise. Okay, so this is the state, and this thing with the differential privacy that I'm not going to talk about today, we put it in production last summer, and this is the list that we send now out, okay? So now what's the problem even with this approach now is that clients are more happy because this differential privacy approach tries to eliminate the leakage of revealing what we did yesterday with our clients. However, from the bank side, this is not great now because still we are sending our inventory in the clear, right? So even like for some stocks, we say, for example, we have this many shares of Apple, right? So even if it's noisy, we are still leaking that we have Apple, right? So we're still giving out some leakage, right? So what we want to do now is like to give a solution which is completely private, where we don't want to actually leak anything. And you could think you're all have crypto background, right? Okay, great. So you would think that we can encrypt it, right? So now if we encrypt it, I mean, if we send to the client an encrypted list, they cannot see anything, right? So now we have to also ask the clients to encrypt and send to us also what they're willing to do. And then what we're trying to do, we're trying to match to see if we can fulfill 2 orders, okay? So here I have an example. So let's say on the left side, we have the inventory of a client. And on the right side, we have the inventory of the bank, okay? So in this example, if they both submit these encrypted inventories, then if we run the algorithm, which I'm gonna tell you later what's this algorithm, then what we're going to end up, so we're gonna give the first client for Apple, for example, for the first symbol, we're gonna give him 100 shares, because if you look here, we had 800 shares of Apple, okay? And you see now our new inventory is 700. By the way, short here is for sell and long here is for buy, just to make it clear. Okay, so what is revealed here? So whatever we didn't match, we don't reveal. So we will never know, for example, that the client asked for Google 500 shares. We will never know that. So only what is being matched is being revealed, okay? So what we can have here, we can have privacy for the bank because nothing is revealed unless there's a match, and also privacy for the client. So the client is sure that whatever we cannot match, we cannot know what he asked for, right? So this is the example. And here, what I'm gonna show you the demo now before I go to the solution. So here I'm repeating some things that basically we want these privacy guarantees for the bank and for the clients. And also want to achieve malicious security. So we don't want to have this semi-honest security, right? You understand why we need to make sure that the clients don't cheat and try to learn inputs of potentially other clients. We want it also to be efficient. And also we have to integrate it with the platforms that the bank has already. And the solution is to use secure computation. Also, we wanted to have a solution where the clients don't have to download a lot of things, right? So we used a web-based version so that they log in and they can actually start doing this. Because if you start telling them to install packages, it's going to be a mess. So that was another requirement we have, and also like make a more optimized solutions to make it run faster. Okay, so these are some practical details here. So let me show you the demo before I show you the solution. I have a video of it. So this is running every day, every half an hour. So here I have the video. Okay. So this is like, you can see it, right? Yeah. So this is something which is called JP Morgan Markets. As you see it here at the top, it's like a platform that JP Morgan offers to clients, like to hedge funds, and they can do many things. Like you can see the list here. There are many different applications that the bank has. So our applications is in the prime brokerage. And here we have this PrimeMatch here. So, and here again, I'm showing you the client view, okay? So what the client has to do to participate in this computation. I'm not showing you the server of JP Morgan. I'm showing you only the client experience, okay? So potentially he has logged into this JP Morgan Markets, and that's the screen that he sees to run it, okay? So what he has to do at the beginning, so he needs to upload the file of his inventory, right? So it can be an Excel file or CSV file, whatever. So here I'm opening the specific one. So we will see in a bit, what does it include? Okay, so now it's loaded on the browser. And again, this is the browser of the client, okay? Everything is happening on his browser. So here, this is what is the file. So as you can see on the file, first column is the symbol, what stock we want to do. Then this is like the name of the symbol in some particular like system, and this is the Bloomberg system, okay? Because some symbols might be called differently under different systems. So we want to make sure that we are talking about the same symbol. The direction, if it's buy or sell, okay? Short is for sell again. And now we give two quantities actually. So we give the first quantity, which is the number of shares, is the minimum number of shares that you are willing to accept. And full quantity is the maximum that you're willing to accept. For example, if I cannot give you more than your minimum, then there's no match. Okay, so we ask for two numbers for the number of shares that you want to have.
Just a quick question.
Yeah.
Should there be some price matching?
Okay, good point. So this one, so far, the price is fixed.
Oh, okay.
There's something which is called dark pool. I have it later on some slides, where you also want to match the prices.
Okay.
But in this one, the price is fixed.
Oh, okay.
Yeah, I'll tell you later about that.
So is the goal to try to fulfill as much as
Okay.
possible? Like,
And by the way, if you have any other question, feel free to stop me. And the ones from the
can we ask questions
from
on
Zoom too.
Zoom?
Okay, so now if we go back, if we come back to the screen, it's the same file. Now you see it on the browser. Okay, you see the symbol here. These things here are again like different systems for the symbol to be represented. So we make sure it's the same symbol.
Actually, can you turn on the audio of your laptop? Because I think Dylan is asking a question.
Oh. Elaine, can you repeat?
I was just wondering, basically you submit this form and the bank will try to fulfill as much as possible. Is it, if I have the full quantity, I will try to fulfill the full quantity. But if I don't have enough, I will check the minimum. And if
Yeah,
it's-
and in fact, we first check the minimum and then we go to the maximum, because if we have 5 clients coming, we want to first satisfy all their minimums, and then we go to the full, so such that we have more chances to give inventory to more clients, because maybe if we give the full quantity to one client, then there's nothing for the other clients. So it's like a fairness solution. So we prefer to first exhaust all the minimum. So first we check your minimum, then we go to the next client to check his minimum, and then we go to the full quantities. So that's how we do it. Does this answer your question?
So if you can fulfill the full quantity, you will fulfill the full quantity.
Yeah, if we can, yes.
So you're basically just trying to fulfill as much as possible, subject to some minimum quantity.
Yeah, exactly. Yeah. You will see it again. Yeah, I will repeat this again at the end of the demo. So you will see while it runs, what do we mean here? So continuing on this now. So the client uploaded this file. So now you see here the status is like that it's encrypted, and it's encrypted on his browser, okay? I mean, again, I didn't tell you what's the algorithm, but this thing that it's encrypted, okay? And here you see direction, the minimum quantity, the full quantity, and here we will see what is being matched, and the spread is the price that you were asking, but the price is fixed.
Right.
For every symbol is fixed. So if there's a match, the price is fixed. We're just revealing the price, okay? And in fact, the client even knows the prices beforehand. So it's something public. Okay. So now the client has to register. Like register means that he's sending this to the server of JP Morgan. And now that he submitted it, so here you can see that in 53 seconds, we're going to start this matching. And at the beginning, it does some like filtering. For example, here I put some fake symbols. So if there's some fake symbols, we don't consider them. So you see it's already, it says no match already, because the symbols are fake. And these are some other symbols from some other like regions that we don't support. So also it kicks them out. So it can also do this process at the beginning. So now we have to wait like 50 seconds for it to run. And as I told you, it runs in production every 10 minutes. So here you see when I filmed this demo, it was 4, and at 4:10 it says that it's gonna start doing the matching. I also put some test symbols from both sides, like from the client and also the JP Morgan inventory, to show you like actually partial matches. So let's yeah.
Is there a specific reason of reading more than it?
So actually, yes. So we are running this twice every hour, and the times is at like the hour at 10 and the hour at 40, okay? So there is 4:10, like 4:40. So you have to be considered in this run. You have to submit by this time. So for example, you can go and submit at 4, then you have to wait for 10 minutes. So what do we do? So we receive all the clients. So here I'm showing you one client, okay? But for example, maybe 10 clients will submit. So then before this time, before 4:10, all the 10 clients must submit. And then once they come, what we do, as I was saying earlier, we process them in a random way, okay? So we all process them one by one. We pick them in a random way, and we first start fulfilling their minimum. So if we finish with all the minimum of all the clients, then we move to their full quantities. So this is how we do it. But it's important because we need to start it at that time. So if a client wants to participate in this one, they have to do this registration before. And because I did this, like,
If one client wants to buy and the other client wants to sell, can you just have one guy sell to the other? Like, let's say
yes,
you don't
so,
have inventory, but one guy
Yes.
wants to sell.
yes. So we also have this, we call it multi-client, when you can actually, let's say JP Morgan doesn't have, so Elaine is saying, what if you want to match the clients? So I'm also going to show you the solution for this one, Elaine, that you are asking. But now in production, we are running only the client to bank matching, whatever I'm showing you now. So the code for the client to client, we just didn't push it to production yet. So this is the demo of the client to bank, but I'll show you the solution also for the client to client.
So how many clients are using this new matching market?
Yeah, so we put it in production in September. At the beginning, we had 4 beta clients, and I think now we have 6. So we are going slowly to show it to clients. So slowly we want to get more clients on it. And once we get more, then we will push the client to client matching. So now
Are
it's like,
Are the clients like some company, or are they individual users?
no, they're hedge funds. So they're companies.
Oh, I see.
Yes. Yeah. And the first 2 months, we also had the beta version where we are telling them here is the application, and maybe they had some feedback. For example, oh, we don't like this button, we don't like this display. So they also do this test. So we also did this the first 2 months if they had something to add. So the first 2 months it was beta testing. Yeah.
The MPC is run on the JP Morgan servers, or are the clients also involved in the MPC?
Yeah, so also the clients are involved. So after this is going to start now, in the background, there are also messages exchanged between the client and the server. So they are also participating. So if the client submits and then he closes the browser, and if he comes again, then we have some methods to recover his state. But if he doesn't come back to send the messages that he's supposed to send for the secure computation, we don't consider him. So you need to keep your browser open. So the clients not go away. Because it's not like a full homomorphic encryption solution where you submit and you go away. It's really like you have to interact. Yeah. So do you want to see? Now it's gonna like start. So now you will see that the time came. So you will start seeing slowly that the orders are being like processed and matched. So let it finish. Okay, it's finished now. So let's go over it. What happened? So now we can see, for example, for the first symbol, we gave like a full match. We were able to give the full quantity. For the other ones, we didn't have what they asked, so there's no match. Oh, I went from the beginning of the video. And I also want to show you partial match. Okay. So here, if we scroll down in the test fake symbols that I put it here, you see here there's for example, partial match here. So he asked, his minimum was 20, his full was 440, and we were only able to give him 300. Okay. And again, this is for one client now, what it ran. And you saw like it was fast, but in the background, it ran this secure computation. And then at the end, you can actually, oops. So now the client, so wherever there is a match, the client executes. So it's being executed, the transaction is happening. But for example, like we will never know here that we didn't have a match for this stock. Particularly, we will never know that he asked for this, either for the stock or for this quantity. So we will never know that he asked for that. Okay. And then at the end, I mean, I just saw on the screen that you can download the result. You can download it as an Excel file that tells you. It's exactly the same thing that we were seeing on the screen. And again, to clarify what is now in production. Now in production is that we can have many clients. As I said, they can come and they should register before the specific time. but we process them in a random way, and we only like process the inventory of the bank with each inventory of the client. We don't do the client to client in this demo, but I'll show you on the slides how we also do that. It's just not pushed in production yet. Do you have more questions about the demo before I go back to the slides? Where are the slides? Just a second. Why I cannot? Sorry, you're looking at my random. Did I close the browser? Oh, here. Okay. Okay. So I'm going to show you now the solutions. So as I said, like there's this two-part inventory where we just do the check between the bank's inventory and its client's inventory. And then there's the multi-party, which is what Elaine was saying, the client to client, when let's say JP Morgan doesn't have the inventory, but maybe we can match the two clients together. And so the thing with the price that you asked earlier, it's like the privacy preserving dark pool. So there is now some mechanism which is called dark pool, where if a client has a large trade and they don't want to post it in the public stock exchange, they can go to these dark pools, and only the operator of the dark pool can see what is the order. However, if you look online, many banks, they had to pay a lot of fines because they were the operators of the dark pool and they still did some front running stuff, okay? So then what's the next step here is to also encrypt the orders that you send to an operator, because this is exactly what we're doing. But in the dark pool, you also have the price. So it's exactly the same problem. But now to do the matching, you also have to check if the price that the price of the buy order is in the range of the price of the sell order of the other person, right? So you need to do more comparisons now to also do the prices. I'm not going to talk about this one. We do some research on that to make it more efficient, because I'll show you some running times here. And in the dark pools, you want things to be extremely fast, okay? And this one that we're doing here, it's like, as I said, it's like an auction thing. It happens twice every hour. It has to be fast, but it doesn't have to be like extremely fast, okay? So in the privacy preserving dark pool, we're still doing research to make it faster.
How many people would you like expect? Like how many participants would you expect?
So this application, it has now like 60 to 80 clients. The dark pools, I think they can have more, because I think in the dark pools also individuals can send orders. So I think when you move to dark pools, it will be many.
Okay.
Yeah. But for this one is 60 to 80, the total. Okay, so here is a slide about multi-party, which I described already. But we can also match these two clients together. Okay. So here are the requirements that we had moving to the solution. So first, we don't want to have any communication between the clients, okay? Because I mean, we don't want, and also they don't want to reveal their identity to the others, okay? So there shouldn't be any message between them. So we have the star topology network where everybody should only communicate to the bank. And we need the support for partial matches and the malicious security, okay? And for the fairness, another thing that we're trying, oh, I need to connect my laptop. So for the fairness, I was saying that we're trying to first cover the minimum quantities of the clients to be more fair, to give more inventory to more clients. But this is not robust, because still maybe with the minimum quantity, we can give all our inventory to some client, even with his minimum, right? So we're having a project using machine learning to try to have different tiers for clients. So based on the tier that you are, we will process your orders based on the tier. But again, this is also still research, and we didn't implement any of that in production. But we would like to have a more fair solution. Let me just connect my laptop so we don't lose power. Is this like
here. Over here.
I hope it works. Yes. So I'm going to start with a multi-party solution. And just to give you a sense of it, with an example, we will go through it assuming full homomorphic encryption, but we're not using full homomorphic encryption, just to show you the example. I mean, you know what it is and don't need to introduce it for you, right? So here's an example that we have here. So we have 3 clients. And again, I'm showing you the multi-party solution now. And the client to bank solution will be a simpler version of what I'm showing you now. I'll tell you at the end. Okay, so let's say we have these 3 clients. The first one has 160K number of shares, the other one has 50K, and the other one 70K. So if we do all this matching, then we can do 75% of the long because we can give 120 to the first one, right? And because we have 120 short from the other 2 clients, so we can give 120 to the first one and fully satisfy client B and C, right? And we will never know that client A should like asked 160, right? Because we gave him 120, so we have no idea if he asked for more. This is the privacy that we want to get, right? Yeah, that we will know, yeah. So we are revealing whatever the output of the computation reveals, right? So since we have to execute it, we will know that, yeah. So only the output is revealed, exactly. Okay, so basically what we have to do here is like comparing the number of the shares, right? So if you think about it, the main computation that you do here is secure comparison, right? Because you have to compare the 160 with the 50 and the 70, right? And also you have to do aggregation too. So we can aggregate all the shorts and all the longs first, okay? And then start comparing, okay? So it's like aggregation and secure comparison. These are the 2 main secure computation operations that we have to do, okay? So imagine now if we had fully homomorphic encryption, it will get all the longs and the shorts, it will add them and then compute the minimum and then between the quantities. For example, it will calculate the minimum between the 120 and the 160. The minimum is 120, so this is how much we give to the first client, right? And then again, it will calculate the minimum between 160 and 50. The minimum is 50, so we give 50 to the second client. And then we are left with 90 from the first client, right? And then we are going to calculate the minimum between 90 and 70, which is, no, we are left with 110, not 90, right? So then we are calculating the minimum between 110 and 70s, which is 70, right? So it's a bunch of comparisons basically, right? And then at the end, we are sending the result encrypted. Let's say the server is doing all of that, and then they have to decrypt, okay? So that's a potential solution using a fully homomorphic encryption, okay? So we don't wanna do that because, I mean, as you know, fully homomorphic encryption is not very efficient. And on top of that, we also need malicious security. So also adding malicious security on top of the heavy computational FHE is also like even more expensive, right? So we don't want the solution. So basically, we're going to focus on how we can do this comparison now in this secure computation fashion using techniques from secure computation, okay? So again, as I was saying here, the main operation is the minimum between the 2 quantities. So from now on, I'm going to focus to the setting where we have a server in the middle, the bank, and 2 parties. And we're trying to match the 2 parties together. Okay, so I'm going to focus on this scenario. And as I said, we just need to compare the quantities that they give. Okay, so we use 2 out of 2 secret sharing as the first tool that we're using. Of course, you know what it is, right? I'm not gonna go into deep details. Okay, and how we are doing this comparison. So I need to show you what our comparison circuit is doing. So basically, the parties secret share the values that we want to compare. So let's say here we want to compare A and B, okay? So they secret share it, and then we are running a comparison circuit, okay? So what is this comparison circuit? Which can be run on the shares, okay? So this is like, there was a secure comparison in the secure NN paper where the setting was the same. You had two clients and a server in the middle, and you really wanted to compare the two numbers of the two parties. This is exactly their setting. It's semi-honest, they don't have malicious security. I'll show you later how we add malicious security, but also we did some, I say here, improved version, because their comparison like required, it works on shares, and it requires some nonlinear operation on shares. So we changed the circuit to have all the calculations linear on the secret sharing, okay? I'm not gonna go through the details, but it's like some improvement over the secure NN, but the algorithm is mostly the same, okay? So imagine for now, because I'm not gonna go to the details of this comparison circuit. So imagine that it takes as input shares of the two values A and B that we want to calculate for every bit of the number. So we get the bit representation of the numbers A and B, and we secret share them. Okay. And then for every bit, we'll calculate the circuit. This here, like it's CI. I'm not going to tell you exactly how the circuit calculates it. Okay. And then we're also randomizing these CIs. So then what the circuit does, so we multiply every CI with some random number SI. So the algorithm says that if there's at least one DI, so I call the result of CI times SI DI. So the algorithm says that if there's one D, which is 0, okay, it means that A is bigger than B. So I think that's the only thing we need for the rest of the talk from this circuit, okay? So think that it gives out as many Ds as the bit length of these two numbers that we are comparing. And if one of them is 0, it means that A is bigger than B. Okay, if there's no 0, it means that like B is bigger than A. Okay, that's all we need from here. If somebody is interested in the circuit, we can either look at it at the end, or you can ask me offline. Okay, and the important thing that it's linear calculations on the shares. Okay, so we don't have to do anything non-linear, and it's important it's linear for us because we don't want to have a lot of communication between the servers and the client. Okay.
So the bank is receiving like a mass share.
Yeah. So exactly. Yeah. So I have it here. So that's exactly what you're asking. So the client secret shares his value to two shares A1 and A2. So he keeps A1 for him and sends A2 encrypted through the bank. And then the bank is forwarding it to the other client, and the other client decrypts. Okay, so we assume that there's some like Diffie-Hellman key change between the two parts. Again, the Diffie-Hellman passes through the bank to encrypt the shares. Yeah. Okay.
What is the security model? Is it like a malicious? I mean, all but one corruption, or is it honest majority?
Yeah, so for the semi-honest, so I'm showing you first the semi-honest version. So in the semi-honest version, it's like everybody's semi-honest, and you can have like collusions. Two parties can collude, but yeah, two parties can collude, yes. And they will not leak any information. So that's the collusion setting in the semi-honest. And when I come to the malicious, in the malicious one, you cannot have collusions.
So
but in the semi
only against a single deviation, like in the malicious one.
Yes.
I see.
Yeah, I'll show you when we go there. Yeah. Okay. So here now, as a first step, we secret share the two values. And then, so this min flag here is this circuit that computes the minimum between the shares. So the first party runs this circuit that computes the minimum, that compares the values that I showed you here, but we don't need to know the details now. Okay, so they run this circuit on the two shares, the share that they received from the other party, B1, and their own share. Okay, so both parties are doing this. They are running the circuit. And then if you remember what I said is that this circuit gives out shares of these D values, right? And then the server has to add the shares and again search after he adds the shares. So every D here is a vector of these where the vector size is the bit length, okay? So it adds all these entries in the vector like coordinate-wise. So this means that he reconstructed all the Ds at the end. And now if it sees a single zero among these Ds, it says that A is bigger than B. If it doesn't see any zero, it says that B is bigger than A.
B is like a bit string, right?
Yeah, it's a bit string, yeah. So here, I overload this notation, it means that it's like D1 and D2 are like vectors, where every vector is of size of the bit length. So you do like per coordinates, you have to add them. And then after you add them, you have reconstructed all the Ds. So also D here is a vector. And if there's at least, actually, if there's a single zero, then it means that A is bigger than B. Okay, so the server sees that, and then he announces the answer like if A is bigger than B. And then basically there's another step where actually what we need to reveal is B, right? Because B is smaller.
Yeah.
So the matching quantity is B. Okay. So this is a semi-honest version. Okay. Do you have any question on the semi-honest? And again, here is like, it's a 2-round protocol where in the first round we just secret share. And in the second round, we just send our D vectors, okay? Because this is linear and we operate on shares, we can do like everything locally. We don't need to interact with anybody. That was what I was saying before. It was important for us to make this linear. Okay. So now for malicious security, see how I do them. Okay, so now for malicious security. So first of all, I have to say that you could also make this like maliciously secure using pre-processing. I mean, if you know, like in secure computation, you can have like, you can generate a lot of pre-processed data earlier to use them also to achieve malicious security in multiple ways. However, we cannot have any pre-processing in this application. That's another restriction. For example, we don't know which client is going to come, right? Not every client is coming every day. And also then if we have to generate them, this pre-processed data, we also need to bring them again, like earlier, to generate this pre-processed data. So they will have to commit much earlier that they will participate. And in the real world, parties don't really know till the last minute if they want to participate. So we cannot really use any pre-processing to make this maliciously secure efficient, okay? So that was another issue. So now I'm just going to the solution that we want to use. We are trying to use some like zero knowledge, but lightweight. For example, if you apply zero knowledge on this computation circuit, then it's going to be very inefficient. So we're trying to avoid that, okay? But I'm gonna show you, we're gonna use some zero knowledge to achieve this. So for now, going to the solution, imagine that ideally, so let's say we don't want the clients to cheat, okay? So we are in this setting first. So if, let's say, hypothetically, if the first client can also run the same circuit on the other shares, right, that he doesn't have. I mean, he doesn't have B2, he cannot run it. But if he can run it, hypothetically, then send the answer to the server can check if they both got the same answer, right? So also the other clients, like this blue part is the hypothetical scenario where the parties basically rerun the code of the other client, right? On the other part of the share, right? So whatever the client run here, the other party runs it too, which of course in reality it cannot happen because I don't have the shares in the clear, right? Okay, then the server could actually cross-check that the two clients didn't cheat, okay? So we're discussing this scenario now. We don't want any client to cheat now. But of course it's not possible. However, we're going to use commitments, okay? So we are going to still have the clients run twice, okay? But the second time, you are going to run it on committed values. So the second time, so you have like this, you received B1 in the clear, the first share of the second party in the clear, B1, and the second share, you are receiving it in an encrypted form, like inside the commitment, okay? So now you can run his calculation too, but on committed values. So this envelope here means committed values, okay? So I repeat, what is the change for now for this slide? So the party secret shares the input, and then it commits to its value and to the shares that he has, and sends the commitment of one share to the other party, okay? And the encryption of the other share to the other party. Okay, so one commitment and one like secret shared value. Okay, and this the same thing from the other client, and then they can rerun twice. And again, this is again local computations, right? Because we're going to use linear homomorphic commitments here. So once you run this, you don't need to communicate with the server. You can run this locally because it's linear. Okay, so again, there's no extra communication here. Okay. The size of the communication is increased now because we added the commitments, and also the computation is increased by twice because the client has to run twice now. But the number of rounds is the same. Okay, so now the server is receiving the same calculation on the shares and the same calculations on the commitments, and then he can open the commitment and check if the two are the same. So if they're not the same, it means that one of the two clients is cheated. Okay, because like as an example, let's say I run this on behalf of the first client, right? And I sent my D1 prime here, and the second client was supposed to run the same calculation here on the shares to send to the server. So if his D2 is not the same as my D2 prime, and if the server notices that they're not the same, then it means that one of them has cheated. Okay.
So future T1 prime and D2 prime are the committed commitments of D1 and
Yes.
if they want.
Yes. So we have, so the server, I'm not giving these details, but the server is opening the commitments and then is checking if the opening of the commitment is the same as the D1 and D2. So you open all the primes. All the primes are in committed values. So you open them and then you check that they are the same as the other ones.
So, I'm a little bit confused about like what commitments are used here because the server does not have the randomness of that.
Yes, he doesn't. So we are using some Sigma protocol to get the randomness. I'm not giving the details here, but yeah. So you have to do something more here to make that possible. So we're using some other Sigma protocol to do this, yeah. I can give you more details, yeah. But that's a good point. It's a detail that I'm hiding here. Yeah. But is the general framework okay for now? Okay. So now basically what we're doing, we are running it twice, once on the shared values, one on the committed values, and then the server can check if any of the two clients has cheated, okay? And again, we cannot use pre-processing. For example, you could have asked why you're not using homomorphic max or things like that, or pivot tuples. These are some things that can speed up these things, but we cannot because, as I said, we cannot use any pre-processed data. Okay, so where zero knowledge is coming now? So here we have more lightweight zero knowledge instead of running the whole thing on zero knowledge. So the first zero knowledge that we have to check here is that the client, we need to make sure that whatever he committed is the same values as the ones that he secret shared, right? So basically, this is commitments for equalities. Zero knowledge for committed values, which we need to show that they're equal. Let's say you have two committed values and you need to check if they are commitments to the same values.
So you only have to check A equals to A1 plus B2, right?
Yeah, so and A1 and A2 are bits.
Oh.
So we need to check that basically you commit to A, so you get the bit representation of it, and then we check if it's the same as the sum of the shares, yeah. Okay, so these are like pretty fast zero knowledge schemes that we can use here. This is for the client side, but also now let's go to a cheating server, okay? So for the cheating server, what he can do now, he can start like cheating about the D values, right? Or he can announce whatever he wants, right? So we also need to add zero knowledge here to check that he did also this calculation correctly. However, as I said, we want to minimize like how heavy we want this zero knowledge to be. So now I want you to remember what was the result that the server had to check, right? Remember he was getting all the Ds. And if you could see a D that is a zero, then it means that A is bigger than B. So basically, and all these values are committed to. Okay, so basically what we can use here, we can use something which is called one out of many proofs. That first appeared, I think, I didn't put the citation here. I think it was from, Sahai and Jens Groth, the first time that they introduced this one out of many proofs. And basically what it does, think that you have a bunch of committed values and you want to actually show that one of them is a commitment to zero. Okay, so this is what it does, this one out of many proofs. I'm not going to the details because this part, actually, this one out of many proofs, we're using them completely black box. Okay, so we didn't do any change to this one out of many proofs. We just needed to make it work for these commitments and the shares that we have. Okay, so, and these proofs, I don't know if you are familiar with the running times with this zero knowledge, but they have like very close running times as this range proofs of the bullet proofs. So they are based on this type of technique. So they are not very heavy computationally. Okay, and just to give you, yeah, I think we should finish, but here it was like, I was having the statement, you have a bunch of commitments and you want to show that one commitment is zero. So that you're showing that the parties are not lying. Okay, and for the two-party version is like a very simple, like the generation of the previous solution, where basically now, let's say we have two parties now, right? And let's think that the second is the bank, okay? So in that case, you're doing exactly the same protocol, but instead of secret sharing now, you can send an encryption, okay? So you can set some additive homomorphic encryption where the other party can run the circuit here using this additive homomorphic encryption. So you don't need to do the secret sharing now. Okay, so that's the only change. And then you still need to make sure that you still need to have the committed values, and then also need to make sure that whatever you encrypt is the same as the value that you commit to. Okay, and the commitment here is used for the zero knowledge part. I'm not going through this, just like I'm giving you a high level idea of this. Okay, so basically, just to wrap up the solution for the client to client, we first do like a secure aggregation, which I didn't talk about the aggregation, where we are actually summing up all the longs and all the shorts. And then we are revealing the minimum of the two, because anyway, we know that it would be fulfilled already, right? And then we go client by client, we take the quantities of two clients and start doing this comparison protocol that I just showed you here. Okay, using this like comparison circuit and adding on top the homomorphic commitments and the zero knowledge. This is just the high level. I didn't go to the details. If you want to know more, just let me know. And just, I can give you some running times. For example, I didn't add it on the slide, but I can give you some running times. If you want to know roughly how much it takes to run. So for 100 simples, it takes roughly like 10 seconds for everything. For 200, it takes 20. And like, for example, for 1000, it takes 1 minute. Okay, so the increase is linear as you have more simples. And the number of simples that this current application works in the US, it's 5,000. Okay, so for 5,000, it takes like close to 7 minutes. Okay. If you want to do it, like for example, for the dark pool, okay? In the dark pool, you're going to have like 30,000 symbols or 50K symbols. Like, I think in the world, they're like the ones that they're used in this application is 30K. So imagine now, if you want to take this to the dark pool scenario, it's going to be very slow, right? So that's why I said, because think now, instead of doing comparisons only on the quantities in the dark pool, you also need to do comparisons on the prices. So you need to do yet more comparisons, right? So we are researching that to make it more efficient based on these constraints that we have here. But the new piece here was like this malicious security of the comparison protocol. I mean, you can use it now for other calculations. For example, for machine learning, typically you have to use comparison. But that's like the main technical thing. So yeah, so let me know if you have more questions. I think we should stop here. Are there any questions?
So right now, which part are the most time consuming?
Of the algorithm?
Yeah.
It's like, so it's the comparison, and from the running times that we have, the most, like the one that takes more time is the one out of many general knowledge proofs.
Oh, okay.
That's the most.
But you have to use the like black box. So,
When I say black box, I meant that we didn't change the older protocols. That's what I meant, yeah. We did try to optimize it in the code, but there's no any technical crypto contribution in the one out of many proofs. That's what I meant. But that's what it takes most of the time. And another thing is that, so when you can process the symbols in parallel, that's another good thing. So for example, these running times that I gave you, they are not for like super powerful machines, okay?
okay.
So if you also want to throw like more powerful machines with more threads, then you could actually parallelize and run for many threads for many different symbols, because one symbol with the other, they're not related, right? So if you have really very powerful computers, then you can solve these problems if you want to exceed, actually, if you want to go to 30K symbols. If you really want to throw a supercomputer here, like a computer that has a lot of like multi-threading, then you could get a good running time. But we want to also like do it. I mean, if it comes to that, we can do this, but we do want to like research some more efficient solutions.
How about the zero knowledge proof use client side when you use the proof to prove that you're sharing properly?
Yeah, this is like a similar version that appeared in the bulletproof proofs. Like basically you need to compare their like if two commitments commit to the same value. So it's like that we use Pedersen commitments here. So you just need to check if two Pedersen commitments commit to the same thing. It's like pretty standard proofs that they're being used heavily. So yeah, they're not taking too long. Ideally, we'd like to kick out any zero knowledge, but the problem is that we cannot use any preprocessing. And another thing here was the challenging part was that you only have a server in the middle, right? So if you would allow to have more servers in the middle, or like make the clients communicate, then you can have like more efficient protocols.